Welcome to TechPacks. In today's video, we'll delve into an exciting project that combines artificial intelligence with physical computing, an AI-powered chatbot using an esp-32 microcontroller designed to bring a 3D printed face to life. The primary aim of this project is to create a lifelike chatbot capable of expressing human-like emotions through movements controlled by an esp-32 microcontroller. This is achieved by integrating AI to respond to user queries and control servo motors for realistic facial expressions. With the rise of AI in everyday applications, creating interactive and emotionally expressive chatbots can enhance user experience in various fields, such as education, customer service, and companionship for elderly or isolated individuals. This project showcases how technology can bridge communication gaps and provide engaging interaction. Let's move on, the most exciting part, that is demonstration. Let's see how it works. At very first, we have to run the Python code.
Hi, I'm Robot. How can I assist you?
Let's ask some question from Humanoid Chatbot. What is artificial intelligence?
Artificial intelligence, AI, refers to the simulation of human intelligence in machines that are programmed to think like humans and mimic their actions. AI can be categorized into various types, including machine learning, where algorithms are used to learn from and make predictions on.
Tell me something about Canada.
Canada is the second largest country in the world by land area, spanning over 9.98 million square kilometers. It is known for its vast wilderness, numerous lakes, and diverse landscapes ranging from the majestic Rocky Mountains to the rolling prairies and...
Who are you?
I am Robot, created by TechPacks.
Go offline.
Okay, I'm going offline. Have a good day.
That is all about the demonstration. So now we will see the real structure of our robot. The mechanical assembly of our AI-based humanoid real chatbot is divided into 5 main parts: the neck, jaw, eyes, head and ears, and front face with nose. Let's begin with the neck assembly. The neck assembly is crucial for supporting the head and enabling its movement. We have a base plate where 3 neck rods are mounted. These rods are designed to provide stability and flexibility. Each neck rod features a ball joint at the end, which allows for a range of motion. These ball joints are connected to a central socket, which is equipped with a flat plate. This flat plate is where we mount other assembly. The combination of ball joints and sockets ensures that the head can move smoothly and realistically. Next, we have the jaw movement assembly. The jaw assembly is designed to replicate the natural movement of the human jaw. It includes a chin and lower lips module, which is printed as a single piece to ensure durability and precision. This module mimics the lower jaw and is connected to 2 3D printed rods. These rods are linked to a servo motor. The servo motor uses a cam mechanism to control the vertical movement of the jaw. This setup allows the jaw to move up and down in a lifelike manner, enabling the robot to simulate speaking and other mouth movements. Moving on to the eyes, we use a pair of plastic animatic eyes, which are readily available online. These eyes are mounted on a 2-dimensional movement assembly, allowing them to move both horizontally and vertically. This 2-dimensional movement is essential for creating a realistic and expressive appearance. The eyes are attached to a platform that holds the servo motors and spherical eyeballs. The animatic eyes are affixed to these spherical eyeballs, all of which are printed using a 3D printer. This intricate setup ensures that the eyes can follow and react to the programming instructions, enhancing the robot's lifelike presence. For the head assembly, we use 8 3D printed plates. 4 of these plates form the front of the head, creating the forehead and upper facial structure. The other 4 plates form the back of the head. To add to the human-like appearance, we also include 2 3D printed ears. These ears are designed to look realistic and blend seamlessly with the rest of the head. Now let's look at the front face assembly. The front face assembly is crucial for the robot's appearance and functionality. The nose, front face, and upper lips are created from 2 separate 3D printed plates. These plates are connected to each other and to the inner skull using screws. This setup ensures that the face is stable and can support the necessary movements and expressions. In addition to these main components, there are other essential parts, such as gears, screws, small 3D printed chips, and connectors. These components are used to mount and connect all the parts together. Each piece is designed to fit perfectly with the others, ensuring a seamless assembly process. For some models of this chatbot, we also provide a base box. This base box houses the complete electronic circuit assembly. The humanoid robot can be mounted on top of this base box, making the assembly compact and organized. This base box not only protects the electronics, but also provides a sturdy foundation for the robot. If you're interested in building your own AI-based humanoid robot, you can buy this complete 3D printed kit or any part of it from us. Let's take a look at the components used in this project. First, we have the esp-32 microcontroller, which is the core processor handling servo motor control and Wi-Fi communication. Next, the servo motors are responsible for moving the eyes, mouth, and neck of the 3D printed face. The 3D printed face is the physical embodiment of the chatbot, designed to mimic human facial expressions. We also have the SMPS, or switched mode power supply, providing a stable 5-volt 10-amp power supply for the esp-32 and all connected components. Now let's dive into the circuit design and schematic. The attached circuit diagram illustrates the connections between the esp-32, servo motors, and the power supply. Each servo motor is connected to a digital output pin on the esp-32, while the SMPS ensures a stable 5 volts power supply to the entire system. That is all about circuit explanation. Now, let's talk about programming part. We have two programs. One is for the esp-32 to control the hardware part, and second, we have Python code, which is our software part. Now let's discuss Python code. Importing libraries. Essential libraries include GTTS for text-to-speech, SoundFile and Wave for audio processing, Time and Threading for real-time actions, NumPy for numerical operations, Serial.Tools list ports for serial communication, WinSound for audio playback, OpenEye for GPT-3 integration, and speech recognition for voice input. Serial communication handles communication by encoding commands for the esp-32 to control servo motors based on calculated positions. Motor movement converts desired positions into servo motor angles and sends these to the esp-32 for physical movement, crucial for lifelike lip syncing. Phoneme mapping maps phonemes, speech sounds, to specific lip positions, ensuring accurate synchronization between spoken words and lip movements. Integrated AI, GPT-3, uses OpenAI's GPT-3 model to generate intelligent responses based on user input, enhancing OBot's conversational abilities. Speech recognition captures audio from the microphone, converts it to text, and processes it to determine appropriate responses from OBot, enabling interaction via spoken commands. Main function initializes all components, connects to the esp-32, and starts the interaction loop, where OBot listens, responds, and moves its lips in real time, creating a realistic conversational experience. This code integrates multiple technologies to create an interactive humanoid chatbot capable of natural speech interaction and lifelike facial expressions using servo motors controlled by an esp-32 microcontroller. Now let's see the programming of esp-32. First, we include essential libraries, esp-32 servo.h for managing servo motors. Next, we define the pin mappings for our servos, mouth, IV, to ensure precise control over each component of our humanoid's expressions. Global variables like eye center horizontal, eye center vertical, neck center, and mouth close store default positions, crucial for initializing the servos correctly. Counter and last update manage timing and servo update intervals. Upon setup, the serial connection is init, I-aided. Each servo is attached to its designated pin and set to its initial position using servo.write. This setup phase ensures our humanoid starts in a neutral state, ready to respond to commands. In the main loop, the getValue-from-Serial function continually listens for incoming serial data. When a command is received, the mouth servo immediately moves to the specified position using servo.writePo. This periodic update creates a more lifelike interaction, enhancing the robot's expressiveness. This script forms the backbone of our project, enabling real-time control and expression through synchronized servo movements. It's an essential component in creating an interactive 3D printed face capable of emotive responses, making our humanoid robot more engaging and lifelike. Now let's discuss the results. The AI-powered chatbot demonstrated its ability to engage users through natural and lifelike interactions. The servo motors provided smooth and realistic movements, while the AI responses were accurate and relevant, enhancing the overall user experience. In conclusion, the AI-powered chatbot project demonstrates the exciting possibilities of combining AI with physical computing to create engaging and lifelike interactions. If you found this project intriguing, please like, share, and subscribe to TechPacks for more innovative projects. Visit our website to purchase the complete package. Browse, select items, and click on Buy Now. Fill the required fields, then securely proceed to checkout, and you're ready to begin your project journey. Explore our site now to get started. Thank you for watching, and stay tuned for more exciting content from TechPacks.